Hello. Yeah. Welcome everyone to the 5th day of the school. The first lecture will be given by Daniel from ATS Zurich. So, over to you.
Thank you. Okay. So, well, on the first lecture, what we saw was how for these long-range interacting spin systems, for example, not only mean field was becoming exact. Well, so we had a phase transition one dimension, even if we're supposedly not to be able to have. Mean field became exact. And then we also saw an exotic, if you want, feature, which would be the ensemble inequivalence. And today we're going to look basically when the interactions are not so non-local, so not fully connected, but a different regime, and see when is it that we have this transition that suddenly one-dimensional systems can have phase transitions, when is mean field exact, and so on. In order to do so, what I'm going to do is take my typical Hamiltonian, which is the Ising Hamiltonian, and I'm going to try to derive a continuous theory out of it and perform the typical analysis that one does. Like, for example, we know in phase transitions the system will be self-similar, so I'm going to do scaling analysis, and then also a bit of perturbation renormalization group to check about the critical exponents, and with this we will conclude when mean field, the system becomes mean field, which we will see does not need to be fully connected, but the critical exponents are well described by mean field even before. I hope that not everybody knows how to do this mapping, because my idea was to first do this mapping. But if everybody knows, I am kind of a bit sorry. So, as everything, at least I have been doing here, everything is going to be about doing this Haber-Stratonovich transformation. Is this correct? Okay, yes. Which basically is an identity of Gaussian integrals, right? But one can extend it when we have many more variables. Right. Okay. Let me say this one. Let's put an SI. And then it goes this thing. Okay, I will not explicitly show this, but we can at least give a couple of, if you want, intuitions why this is correct. So, say I don't have this term, right? Then I will not have this one. Think of it that it exists, no? A rotation. This is a matrix, basically. If this was an orthogonal matrix, which will be because we want ij to be connected the same way as ji, it exists a transformation, say, where this sum of here just becomes diagonal, right? And just diagonalizing this matrix, and basically the integral becomes of this form, and it's just a collection of Gaussian integrals, which we know that they give 2 pi 1/2 divided by lambda n. And if I have all the lambda n's, this is the determinant, right? All the multiplications of the diagonal. Okay. Why do I do this? Sorry. Again, as always, to disentangle the interacting part when I want to compute my partition functions. Okay. Now, different from the case, sorry. that we did before. Now when I do this, I have to introduce many copies of this Haber-Stratonovich, right? Because before, for example, I only needed one, everything was connected. But okay, let's do it a bit explicitly. And now, okay, so. Should be S, well, S. S understood as the vector. There's one. Okay, I'm not sure if, probably this everybody knows it, but now when I did this Haber-Stratonovich, again, as when we did the other thing, I can compute this, which was this, the trace, right? Anyway. Okay, I should say, sorry, this is an introduction of notation where this implies the product of this dx by 2 pi. Okay. Well, with this, we almost have it, right? Because I wanted a continuous theory where I can do my scaling analysis, and it looks like I'm getting there. Something which is a bit irrelevant, so it's possible that sometimes I write it and sometimes I forget. I hope nobody gets mad. Some constants, blah, blah, blah. Okay. Okay, well, it's going to be the same for everyone, so let's leave it like this. So, to easy my life, I do, again, a linear transformation. Well, it does not need to be nonlinear, but linear. Could be that it scales a bit, the thing, but it will anyway give me a constant, right, that I can absorb from this integral. And then I have basically already written my partition function in terms of a continuous theory, right? I have my hopping term that connects my different fields that I had to introduce with my Haber-Stratonovich. And then I have this term that mixes a bit everything. Now,
that from the lower port, the first line,
sorry?
this expression, how do you get from there?
So, okay, let's go 1 second. So when I do this Haber-Stratonovich thing, right? My typical interacting term between two spins, Si and Sj, I substituted it by an integral, where now I have some variable that I need to integrate, which is the x, and now this is linear with S, right? It only contains one S. So basically this part, I got rid of it by substituting by an integral, and then the linear part, x transpose S, which comes from here. This is not like a multiplication. So Now this sum, I still need to do the sum of all possible configurations of the spins, which is here. But this is, as I did on the first lecture, right? This is for the first spin, when this is plus, and when this is minus, this one, right? And this is just a cosinus hyperbolic. So I have n copies of this cosinus hyperbolic because I have n spins. But in here, okay, you're right that if I'm still having the xi, I should put that I'm still summing, like the n copies, right? And this part, it just comes from this part. And these are just constants in reality. Let's maybe not write them because I think sometimes I didn't write them, so anyway, they're irrelevant, no? Constants will. Okay. Everybody has seen this? No, or yes? Oh, well, in reality, just to say that I'm doing the same as the short range, right? But you'll see that the continuous theory I will get will be a bit different. It's basically what Nicolo kind of explained a bit in the first lecture, but not so much.
So ask them how many of them have not seen this?
How many of you have not seen this? Only you? 2, 3, 4, 5. 7, 8. Okay. Then,
This way the number increases. This way the number increases. Because we don't want to say that we have not seen something.
okay, so it's a bit more than 8, probably.
If you have seen it, then it's
Okay, I see. The trick of an experienced lecturer. Okay, then I'll continue doing it, if everyone's okay with it. Okay, so because this is very complicated and I am lazy, and later we will justify that I can do this, I'm going to just expand this cosinus, this log of this cosinus, as some expression of this form. Okay, and we'll only keep the first 2 terms. So now I get something very ugly, but okay, let me see now my right, and this would be a continuous action with and to be fair, when I prepare the lecture, I put the H and I literally put some note. Don't put the H because at the end I'm going to look at the continuous transition, and up to here H is equal to 0. Maybe I should not have put the H at any point, but okay, let's take H equals to 0. Sorry for this. This one, and then the order 4. Okay, so we're almost there because, as I mentioned, I want a continuous theory, and moreover, since these Jij's were going to be my power law, so. And now, let me put instead of alpha t plus sigma, but I think Nicola also put d plus sigma, and I'll tell you why I put d plus sigma. Before we said that the system were non-extensive when we had, for a one-dimension case, alpha smaller than the dimension, And I said, whenever it's non-extensive, mean field is exact. And since I want to see when, which is the transition, that mean field will be exact, which I will tell you now that it's going to be a bit before, I'm going to put just already the D, right, to ensure if sigma is positive that I am where the mean field cannot be exact. Okay, and 0 if I is equal to G. If not, it diverges. Okay. So, let's exploit translation invariance to go into momentum space, but this I just write it for you to know what I'm doing, but not so irrelevant. And if you allow me also, let me say that in here I never really made use that the system was one-dimensional, right? I mean, if it would have been of higher dimension, I could have still have done this. The only thing that would have changed would be, well, for example, in this case, the dimension, but for the moment, everything was general. And let's do the interlude. Maybe better, right? The tiny interlude that I wrote here, which is, since we went to momentum space, let's look at the Fourier transform of this. Nicole already said it, but let's remember for a moment. A possible crack scaling factor and something of this form, if it's one-dimensional. Now, when I expand this is a sum, right? And I'm going to look at a small momentum k. I want to go into the continuum. I'll take n to infinity. This is going to be, which I will already put a tc here. It will be the constant, but I name it tc because I want. Plus, I don't know. So some, yes, that's why I wanted to say this, exactly. Why I'm putting this A? I'll say 9. Right? I'm counting the distance, so there is like in between each neighboring sites there is an inherent distance, right? Which I'm gonna phrase it A. No, like I think the typical spacing you name in crystallography, just to say that in reality, if A is different, these values are different, right? But just to mention it. Why is this important? As we said before, since now I'm going to later look at how the system scales when I zoom in or zoom out, I need to kind of keep track of how are the coefficients, let's say, the CAs scaling after I say, I don't know, I take the interparticle spacing A to 2 times A. This is for alpha I sigma greater than 2, and this is going to be for alpha, what am I saying? Sigma, sorry. No, I'm saying the opposite. Sigma smaller than 2, sigma greater than 2. Just to say that the first coefficient in the Taylor expansion, one is non-analytic, which is this one, which will be very important that it is non-analytic, and one is the analytical square, which is the typical one you get also in the short range when you expect the cosinus. But why I wanted to say the interlude, because I think Nicolo didn't mention, right, that what happens when I also have the scaling factor is that my sum, which now let me put an n, it becomes something, I don't know, some constant divided by n, r equals to 1. Did Nicolo explain this case? I think not, right? So when I had the scaling factor, right, this n of alpha was going to be 1 plus minus alpha. Okay, alpha being d plus sigma. But since I want to look at negative sigma, I'm using the alpha notation. Hopefully it's okay with everybody. Just why is this important? Because now, if you look at this part, for example, this you can approximate, typical scale by n. There is a dimensionless variable. It's kind of an integral, right? Well, I'm going to approximate it at least by an integral. And if you want, you can use your Mathematica or whatever code you like to use. Or you can even do just do the sum by yourself in the Mathematica. And you take n to infinity, which is this expression when you take n to infinity. And this, even if I took the thermodynamic limit, it will give you a discrete energy level, well, energy levels, discrete values. So, when now I said I want to map it to continuous theory, you see that when I map it to continuous theory, I get some k sigmas, k to the 2, and I say that this k is continuous. In this case, I cannot do it, right? Because it was discrete. Which also, when we now write the continuous theory, will explain us also, or give an intuition, why mean field will be exact. Okay.
I just wanted to recall, which term, that term or this term, whatever, the one that you are approximating by an integral, this term, yes. So there are two ways that I can approximate it by an integral. One is that when n becomes large, the terms become close to one another, and so I write that sum as some constant plus an integral. This is one possibility. The other possibility is the way you have done it. So I guess these two approximations are valid in different regimes. Right?
Well, so what do you mean? So in this one, right, if you're taking the R and N, you're evaluating like, I don't know, you're summing something, right? When you do this integral, what you approximate is that the sum of these points is equal to these areas, right?
No.
But now I'm getting them closer, and I'm dividing by the whole area, right? So
so one thing is that in the original integral you did not have this r by n to the power alpha, I guess. No? You had just r to the power alpha.
Yeah. In the original case, right? Since I don't have the n equal alpha, I don't have this, and I don't have this one.
Exactly.
But then the point is that, okay, let's say that I don't have them. For a sec. Now, let's look, for example, at n equal to 0, right? This is the sum of one.
I understand what you are doing.
Yes.
Okay.
Okay, sorry.
Suppose you did not have that n to the power alpha. Okay. Now
Yes.
there are two ways in which that sum can be approximated by an integral. One is that when capital N is very large,
Yes.
the terms in the sum, the later terms in the sum come so close to one another.
All of them, yes.
That I replace that sum, that discrete sum,
Exactly.
by some constant term that goes from r equal to 1 to some r star, and an integral that goes from r star to n by 2. I do not have to do any scaling. This is one possibility.
Mm-hmm.
The second possibility is what you have done.
Yes.
So I guess these two things are valid in different parameter regimes. Because in one case, what it says is that the terms in the sum come close together for large n. I don't have to do any scaling, just the term itself.
Yes.
So this is one possibility. The second possibility is the way you are doing. That here what is happening is that the arguments are coming close together.
I know what you. Yes, but also the values, no, I guess, are coming close to.
In the first case, the arguments don't have to come close together.
Yes.
Because the arguments are arguments.
Yes, but in...
So 5, 7, 8, 9, 10, 11, whatever.
Exactly,
but
yes.
the terms, when evaluated as those arguments, come close together.
Yeah, in this case I have the terms that they're coming together, and since basically it's like I had the terms extended to infinity, if n is infinity,
Yes.
but since I am rescaling it now, that's why my integral range up to only 1/2.
So these two things are probably valid in different regimes of alpha. Because in one case,
I think probably...
I think something happens for alpha smaller than 1, and I seem to remember that there was some subtlety that is mentioned in this review of Niccolo with...
Yes, but see, in this case the good thing is that for alpha greater than 1, anyway you can do the sum. Because it was, you have something of e to the I r n, no, something, yes, sorry. And then, no, something like this, right? E to the I r, and this is the polylog.
Yes.
So at least for this case,
It can be done.
you can already do the sum analytically up to infinity, is the polylogarithm function, and it's just that at some point the sum does not converge.
But you got my confusion, right? That in one case the
Yeah, I think so,
arguments
but...
are close together, and in the other case the arguments are where they are.
Yes.
But the terms, when evaluated as those arguments, come.
I think you say, for example, there is this one, no, that let's say that they're all equally spaced.
Yes.
So, and you are approximating, and I'm summing this, this,
Yeah, they
this,
are
this.
more or less,
Then it's the same as doing the integral of the one in between, kind of,
yes.
times the spacing, which is 1.
This
This is the one you're saying.
Exactly. And yours
Yes.
is, in your case, those x-axis.
In my case, kind of what I'm saying is, because when I now take it to infinity, it's collapsing, suddenly it has become kind of continuously, no? All the points are super close, and I'm integrating this area behind the points.
Your arguments have also come close together. Because your arguments.
Yes, exactly. So it's like, it has become dense, it's become dense, it becomes kind of continuous.
The x-axis becomes continuous.
Yes.
But in my case, it is still discrete.
Yeah, I know. Now I understand what you mean then.
Can you please check at some point and we can...
Okay.
Now, at some point, I said. So maybe...
Yeah, now probably. Okay, just to then finish it a bit. We had which terms? A term like this. That goes into, because this depends only on the difference, or this should be J, into a term like this. And for the people that they already seen it, this is basically why the continuous theory is going to be different, right? And a term like this. Well, sorry, I should write all of them, I think. You'll see that what I'm doing is a lot of approximations. Okay, and then the last one. Which is the same as this one, but just to the fourth. It's going to be K1, K2, K3, K4. And then, okay, J. A bit annoying, but okay. Now, I should already go there. At the end, when I look at phase transitions, right, what I want is my system to, let's say, present long-range order, or suddenly all elements have magnetized, right? So what I mean is that I'm trying to look at large scales, so when k is approaching 0, which basically means that whenever this I take this expansion of these guys here, which will be 1 minus k sigma, okay, sorry, this Tc minus this k sigma. I always gonna take the lowest order, just to say that all of these products, I will take it as 1. And also this one, I will take it as 1. This one I will still keep it because it will be the lowest one, right? This is the first k to the sigma from this guy. So, now my theory is something of this form. Tc, T, because I chose to say Tc before, now you'll see why I chose to say Tc. 1 minus, remember I'm forgetting to write it here, but remember I want to keep track for the moment, at least of this A to the sigma, but anyway. Then some constant. Oh, I'm a bit out of Blackboard. Let me put it here. And the one, which is just this 1, but when I cancelled everything, it will be 1, right? Okay. The sum of all k has to be equals to 0. K1, K2, K3, K4. And then some Tc to the 4. Okay, almost there. Now, what I want to make is this guy dimensionless, so I take from A to the D plus sigma to A to the D, and I have a theory which is, so basically, have you seen, it's exactly the same, where is this, Laplace? Exactly the same as the short range one, the nearest neighbor one, and the only thing that literally changing is that now I'm taking only a k to the sigma, and then some other factor. Maybe I stop writing all the factors if everyone is okay, because at the end it's a bit irrelevant, as I'm gonna now substitute everything for just new variables. Almost there. Almost there. Let's just now go to the continuum, right? Which is, let's take A to be small and the volume to be large. Substitute sums by integrals. And define what is going to be my new parameters, or my parameters of the continuous theory. Note that they depend on the temperature. This one. Important. Okay, this is more about, in reality, the scaling, because I forgot about all these constants. This is sigma, I set it to 1, and that's it. And finally I got my continuous theory, always a constant, which nobody cares. And I have the phi to the 4 theory of the Ising model, which is also the same as for the short range one, with a very important difference, which is that this does not need to be k-square. And also, maybe I should have said it before, this is a bit of a mistake. It has to be understood as the absolute value, right? Because my model is the same to the right and to the left, right? So it cannot be that the ones for k positive are different from the ones to k negative. It's translation in variables. And because I'm a bit lazy, even if I had it on the notes, and it's a bit, let me just write this in position space. Also, let me put a 4 factorial. It's a constant, so who cares? It's a constant. But for later conveniences, it's very useful. So, finally, we have our Ginzburg-Langdon theory, but a bit changed. So now what happens, for example, below TC? The R0 becomes negative. So now a bit in terms of field theory, it's just telling you that the mass is becoming negative. So now if you think, for example, of what does it mean to have a negative mass? That it costs no energy to create excitations, right? So that's why I placed now, you understand now the motivation to name that constant TC, right? It's kind of telling you when you're going to have the phase transition. But okay. Everything fine to here? Nothing new in reality. The only thing that has changed is the sigma factor there. So let's just start doing physics, let's say. Now what is my kind of order parameter is my field, right? I want to know, for example, when the expectation field becomes non-zero. It's in analogy, if you want, with the magnetization. So at the mean field level, there is no notion of a spatial structure if you think of the spins, right? When you do mean field, you substitute the interactions, but okay, instead of having nearest neighbor interaction, I interact with the overall mean field value. So basically, the mean field level in reality is saying that your profile sigma of x, if you like, is going to be constant, right? This mean field, to assume this. Or to say that sigma k is non-zero, let's say, only for k equal to 0, and all the other ones are 0, right? It's the flat line. Okay, so at the mean field level, nothing changes from the nearest neighbor one. Of course, right, at the mean field level, I'm forgetting about the spatial structure, so I get the same as before, which is something, okay, you had something of, it would be that your S mean field. Okay, sorry for this. At the mean field level, which is giving me something. Did I do it correctly? Now I wonder if I did it correctly. I think there should be a 6 here. Okay, so it has sense, right? At the mean field level, I only get a non-vanishing order parameter when my mass has become negative. Then one can get critical exponents, which I will not derive. I think I'm going a bit slow, but let's write them if you want. Okay. Anyway, I think since I'm not going so very fast. This is until 11, right? Okay, so whatever, some critical exponents. Let's go a bit faster in this case. So what you do afterwards, and then we'll start to see difference from the short range case, is we look at Gaussian fluctuations, no? What does it mean to look at Gaussian fluctuations? It's kind of, we're gonna linearize, right? I take my fields and I say, okay, now I'm just linearizing the theory. I'm just gonna keep it up to quadratic order, basically because since by definition the mean field value is gonna cancel the linear term, and I get some S is equal to some S mean field, and then I should keep track of the dimension, because I want to do, at the end, since I was saying that it generalizes to different dimensions, I wanted to keep it. Sorry for forgetting, as I said, I am a bit sloppy always. Okay, now this should be, well, 6 in reality, but, and my k to the sigma. So this is a Gaussian theory. We can compute everything. We have fixed theorem. Everything applies. What's one different with respect to the short range case is that now we should look at how this is going to scale. This scales as, if you want, k is in correspondence with the inverse of distance. So in terms of a correlation length, this guy is scaling as a correlation length to the minus sigma, right? So this part here has to scale in the same way, right? You have to have the same dimensions, so they scale the same. Another difference, right? For short range, this should be 2, but in this case, it's not. Okay, so one tried to look at the correlations. How do they decay of these fluctuations? And this, I will not do it, but okay, maybe I should, but then I will not. This is nothing but of this partition function, so partition function understood as minus S mf minus these S Gaussian fluctuations. But okay, let's write it down in momentum space, maybe better. Okay. This is the solution. So, nothing new. I'm doing the same as you would do for the short range, but with the sigma now here instead of the square. How does it look? Okay, I'm running out of. But in reality, we're interested into the GR, which is the Fourier transform of this, and it will have an exponential decay when this is large enough, as expected, no? But when we are approaching the phase transition point, we expect long-range order or quasi-long-range order. So we expect to have some either algebraic decay or some constant thing. Just by dimensional analysis, when this approaches to 0, k, as we mentioned, it's in correspondence to 1 divided by x. So this should scale. Okay, sorry, let me write this. I forgot this. As I mentioned on constantly. I'm just writing this because to point out that I still want to keep track of the dimensionality, right? It's not the same result for 1 dimension and 2 dimensions and so on. So this should go as d minus sigma. Okay? And now I should go there. Any questions so far? Is it too known, this? Well, before 8 people said no, so I'm taking as 8 people are profiting from this, which is enough. Okay. Now for completeness, let me write down the short range one, because at the end, as I mentioned, maybe I didn't mention at the beginning, but I'm going to try to explain and justify this effective dimensionality approach, which is basically you map these d-dimensionals, but I'm mostly looking 1 dimension long-range interactings, and then you say, okay, it effectively is behaving as a higher dimensional system, just by the nature that it's in long-range interactions. As I mentioned, the fully connected has no notion of space, and it was an infinite dimension. That's why it was mean field exact. So just for completeness, I remember that the short-range part is d minus 2, but usually we also include this correction, which is the anomalous dimension. So, first time that we're going to get something maybe a bit more interesting is, let's look at when are fluctuations dominating over, let's say, the mean field value, which is basically is an argument, so the Ginzburg-Landau criterion in this case, that you say when is mean field going to become exact? It will be when these Gaussian fluctuations are suppressed. No? This is like the fluctuations I consider on top of my mean field value. So, a measure of fluctuations is this one, if you like, right? My propagator. So I look, for example, inside my correlation length, which if you want is going to give me only inside this region of space, things are correlated. So I'm going to look at the strength of the field in this region compared to the strength of the fluctuations. So basically, well, in this case the opposite, the strength of the fluctuations versus the strength of the mean field value. Okay? We are just going to use these scalings that we derived here. So we get, sorry, where do I have it? Here. So we get, for the first one, let me notice that this is just g of k equal to 0, right? So we get the, sorry for this. I had a mistake, so I pointed out, sorry. I did a mistake here, right? Because this has no sense. They don't have the same dimension. Should be a minus sigma, right? I need them to have the same dimension. Sorry for this. Okay, maybe start going a bit faster. And then this is constant, right? So I just need to multiply by the correlation length to the d and the mean field value, which, don't know where I wrote it. Well, okay, sorry. Okay, and then note that this also has some dimensionality, because I mentioned that R0 had also some dimensional analysis, because it has to be of the same order of k to the sigma. So we get the following. What is this criterion telling us?
You said that the k to the sigma is valid for a sigma between 0 and 2, right?
Yes.
Okay. So for G of R, when D is equal to 1 and sigma is between 1 and 2, then G of R increases with the,
When G of R,
when D is equal to 1 and sigma is between 1 and 2, you have a positive score.
yes,
That means that G of R increases like that.
yes. But it's if I'm not mistaken, that's just, wait, I did something wrong. No, I thought about this, but I think there was so okay, for example, this is the, let me say it like this, 1 second. Yes, I cheated, basically. Yes, but I cheated in the same way that you cheat when you do the short range case, right? Because on the short range case, you get this one. But see, when you computed the integral, you had to split into a k perpendicular to R and a k that was parallel to it, which you cannot do when you have at 1 dimension. So in reality, what I wrote here, it's only valid for D 2 or greater. But it's what you, so I cheated very badly, yes. But it's kind of, you cheat, then you look at this, and you get the argument, and you say, okay, see, anyway, what I did is nonsense. If I am, for example, when you do short range, you cheat, you get this argument, which is the Ginzburg criteria, you say, okay, what I did is nonsense, unless I am at D equal to 4. So in sense, it's kind of, I'm trying to do the comparison of this short range to an effective dimension, right? So I'm doing the same cheating, because I'm assuming that I am higher dimension in some sense. I get this criterion and then I justify. But yes, I cheated. But okay, what I wanted to say is that basically for short range, maybe we should do it in white, we get the criterion sigma is equal to 2, right? For minus D. So you say, okay, when my correlation length is going to infinity, this thing which measured fluctuations versus the field goes to infinity if this is positive. And that's how we got this thing of the upper critical dimension. But now I got it changed, right? My criterion is different. So for example, if I'm taking now the one-dimensionalizing model that I looked before, this is telling me, this is an argument, it's not exact, as Alessandro pointed out, I'm cheating a lot. It's telling you that my mean field should be exact when sigma is equal to 1/2. Which, if you note, it means that the fully connected that I did the other day was exact mean field. And it's telling you, okay, here will also mean field. Let me advance. Then maybe. Okay, I'm breaking off. Okay. So let me now maybe skip some parts as I am running a bit slow today. And let's do what we mentioned before, that the idea now is to map our low dimensional, let's say, or one dimensional, two dimensional, who cares, long range, to a system that effectively has a higher dimension. So we have this, which is our free energy that depends on T meaning T minus Tc divided by Tc, which is in this sense R0, right? H and mu, which in reality H, I also didn't write it, but let's keep it for a moment if you like, but I will kill it. Okay, this, as we mentioned, it's a density, right? It's per particle, it's per volume. So I expected that if I am rescaling now my volume, or say my unit cell, my density, I have to also rescale it accordingly. And then this is the kind of, if the theory has to be self-similar, meaning that zooming in or zooming out, I have the same theory, basically it's telling me that now I do kind of this procedure, my volume is now smaller or bigger, so I rescale, but also my constants have to rescale in a way that I will have still the same theory. If you want the k to the sigma that I was mentioning before, now it has to be rescaled, but it will imply that the R0 and the U0s are also rescaling, which is basically from all this derivation that we came from the discrete, it's basically explained here, right? If now I take my A to 2A, I also have to scale my new parameters of the theory. Wait, sorry. Yes. So this is the justification for what I write this thing. Okay. So now if I am going to try to do this mapping, basically my volume of this effective dimension problem, but my volume of the low dimension is the same, no? It's the same problem. So I'm going to write notation, let's say, my L of this short range up to the D effective, right? I'm mapping, maybe I should write first the other one to explain. So my volume, right, is L to the D. And I'm putting this label to explicitly say this is my long range model. Is the same, right, as my volume of a short range model, but with a different effective dimension. Right? So now I want to compare my F long range to my F short range, but in a D effective. I don't know if to put it here. I have this equality. I will have new long range, short range coefficients. It's just going to tell me that my L long range coefficients to the D are the same as the L short range coefficients. No. Sorry, it's not correct. I wrote L and it's this just take one of the long ranges L to the df divided by d, substitute it here, the y's, you get it there. Okay, so now let's try to maybe get these relations. So, okay, maybe in reality the formula that now we want to know, kind of, is which is this d effective that will depend on the dimension of my problem and how long range is my problem. No, we kind of want this formula. So maybe a recap. At mean field level, it's the same. And when we accounted for these Gaussian fluctuations, we got a correction, just because we said that the propagator now was scaling differently. So the direct, or the next step to do, if we want some analysis, would be to now compute some perturbative corrections, which we will do with this perturbative RG. So now, who doesn't, we'll probably not introduce it, but who is not familiar with perturbative RG? Everybody's familiar then? You're not. You're not. Okay, I say it a bit because basically, okay, let's go like this. What I was saying now is systems and phase transition are so similar. You zoom in, you zoom out, there's like this fractals thing, no? And you see the same structure. Okay, so now what we're going to do is try to do this procedure mathematically. No, we zoom in, or zoom out, which is kind of like this rescaling that we're doing, and it's going to be a bit different. We check how our theory changes, and then we get conclusions. For example, with this procedure, we kind of were saying, okay, my correlations are changing in this way, which then I check for fluctuations. Okay, it can only sense that you have phase transition for this dimension. But we know that we have phase transitions, for example, before, right? Just that the Gaussian approximation was a bit bad. So we're going to do something a bit better. So the idea is I have my theory, right? Which, if you like, contain some k integrals, right? And some propagators, some terms. So now, in terms of momentum, what is the, before, let's say, I was looking at this microscale, and now I'm going to look at, let's say, I'm kind of averaging at another scale. The inverse in terms of momentum is, before I was looking at high k, I don't know, from a value, and now I'm looking at k, if you want, around a certain value. So the idea is, let's take my theory, integrate out these degrees of freedom. So my z contained an integral, right, over my fields. I integrate out the fields with high momentum. I get a new theory, right? I will get some corrections, some diagrams that I have to compute. I rescale now my new theory. I say, okay, I integrate it out from this momentum, but I want the same theory. So now I take my momentum and divide it by kind of a thing, or make it a bit, like, okay, maybe the picture is, I integrate out this shell of momentum. This would be kind of k. And now I have a smaller, my momentum now ranges from a 0 to a smaller value. So let's scale it up. And I have now the same theory with some corrections that came from the fact that when I integrated this momentum shell, I created some diagrams that generate a correction to the mass and so on. Okay, so mathematically this is, I have my S, which I'm going to define as my S smaller, so where the k's are bound to be smaller than a certain value, my S larger, and then some S mixture that misses both elements. Why? Because these ones are split well, right? Because it's minus k and k, I'm looking at the k, but these ones mix them. So basically when you have an interacting theory, when you do this, it's gonna create you some corrections. So now, let's write a bit of equations. No, this is what I'm doing. Sorry, yes. And now when I take this part, this is going to enter as corrections to this other part. How so? Well, let's define e to the minus logarithm of did you correctly? And let me also say that I can always put a factor here that's going to look like this, because since this term does not contain any small one, it's just a constant, right? So I'm putting it this. Why? Because if someone remembers, this is the typical expression that you want to when you're computing. So if I put this, I'm ensuring that only the diagrams that are closed will enter to my corrections, which is this linked cluster theorem, which I have a proof, but if I can skip it also, of why only connected diagrams come with some replica trick, but maybe we skip it. Just trust me, if you want with this, in QFT you will see that only connected diagrams enter. Okay. Yes. I still need to send reference from the first lecture, so I will prepare. Or I give my notes with the replica trick. Because now I don't know a reference.
Goldenfeld probably has it.
For sure. But I mostly learned from notes from professors, so I took this from the replica trick, I took it from some notes, so I'm not sure I can distribute them. But I can look for some other reference. Okay. Again, then my new S is going to be my small s, right, minus the logarithm of this expectation value, right, of my S. Okay, and now should I do this? Yes. Okay. So let's again, since we're going to do only perturbative things, it's the only thing I can do, expand this term as. These ones only give contributions that are that involve S minus, that don't give, sorry, this should be S larger. And this is the mixture, so it has both. So this one is not giving me contributions to the new theory, that it's only for these ones. So I only get this. And again, I will cheat, of course, again, and I will say that this one is a free theory. I forget about the interactions that happen there. So I will substitute it by just this part. Perturbative, not really exact, but it works. Okay, so now just a bit some arguments. What comes and what goes. This one, first one. S mix. No, I will have, if we remember how it is S mix, is some u 4 factorial k1 k2 k4 right, this was our term, and the one that mixes is when some k's are on the shell that I'm integrating out, and some k's are inside. So I have 4 terms that are of this form. This is 0, right? And I have this one that it's the quadratic one. I don't have any external field, it's 0. 6 terms. That are of this form. This is good, survives. And 6 terms that involve, 4 terms, sorry, that involve, that also die because this is not invariant, right? So maybe I will jump a bit.
There's one thing, so there, the one that you have written in whatever is the color, pink or whatever, so that corresponds to the full thing, right, on the upper line. Because you have included, right?
Supposedly you should also include interactions on the momentum shells, high energy momentum shells, but I then neglect them.
No, what I am asking is that the second line is an exact equality. You have just rewritten the first.
Yeah, just separated, yes. It's just the approximation that it comes here, right? If you would be able to do everything, but no one can, so.
No. You see the first line, z equal to whatever. Then the second line, you are just rewriting the
Yes.
first line.
Well, in reality, I did also a mistake, no, in some sense, because there is also another minus, but since I always have a minus, sorry, this was a bit sloppy. I have usually a minus the s. This part is a positive, but I wanted to put it inside the s, so I have, so just to say that I have this, no? Minus the log part. The minus gives the plus. That's why I also only put it a minus. No, this is, if I want to put it on top of the exponential, it's e to the plus log, which is the same as minus.
So how do you get the denominator? So that was the
This one, but this I put it by hand, right?
okay.
Because this, since this contains no, which I wrote, I'm writing this wrongly, sorry. This should be the high energy cell. Right? This contains no term like this, right? It only, so it's just a constant. Do you know what I mean?
No, I know what you mean, but how do you go from that line to the next line? You are putting in by hand.
Okay,
Why are you putting it by hand?
so I have this one.
Yes, and the bracketed term I write as a log.
Okay. Then I write this as e to the log.
Okay, I see. So now I got it.
But now
You are-
I put minus log of a constant plus log of a constant.
Because okay, fine.
Sorry.
Break up the
I start to see that the time was getting short, so I started to skip everything.
got it.
So, Let's do more, maybe diagrammatics is better, no? This is usually the propagator. So which is the correction that you get is basically we are at phi to the fourth. So it's one like this with some bubble, and this bubble can only involve the high momentum shell, right? And which is the correction to the vertex? Well, this one. Okay? So, maybe I should skip a bit, because I think the message was, what does this new correction do? It doesn't introduce any momentum dependence, right? Here you were K, K, K in this one. So this correction renormalizes your R sub 0. So now my new R is going to be the one before plus this bubble here, which it's better if I do them, maybe I can skip them. The 4 factorial has changed to 2 because I had this 6 that I mentioned before. So 6 divided by 4 factorial, it's 4, but the R contains, maybe let me keep the theory here, 1 second. I contain 1/2, right? So one of these 4 is absorbed. I get this one, and then I need to just, from field theory, this is just the propagator, and since the momentum is free, I integrate over it. Okay. Okay, it doesn't work well. And this one is of second order. So it's coming from this one. And I will not care too much about the symmetry factors. I have it here. So it's of minus nature because we have a minus here. We have this 1/2. One can work it out, everything, but it's not so relevant. We get this one. Again, we have a bubble, so we integrate over momentum. But note that we have 2 propagators, one on the top, one on the bottom. This one should have momentum k, is minus k, so we have 2. The propagator squared. So now what's the idea behind is what we were saying, no? What I was saying. I should put like an R. Yeah, okay. 1 second. Okay. Maybe I should start to go faster. Okay, let's look at the scalings. I'm going very slow, sorry. So this was on a very, very long, K was very large. I was integrating the high energy momentum modes. So K was around a value that I call it sigma 0. So basically I can substitute the integral by just saying, okay, the volume of this sphere into the sigma, and then I just substitute by a number, right? More or less. And I can do the same for the U. Maybe I should quickly say the idea and that's it. Now I try to, and I could do the same for the U. I just wanted to flash maybe the result. Sorry. One second. Okay, maybe let's write it as the okay. Quickly say it and that's it. So now if I would rescale all the variables, which I quickly don't show it, sorry, you trust me, I get that my new R, okay, I need to also remember how I'm sorry, I'm stressing a bit. This R0 had and the U0 had some scaling, right? We saw it before from the fact that the theory had to be scale invariant. So basically, now I'm trying to do the last part, which is I want to get back my initial theory. And I integrate it out, let's say from 0 to the outer shell, and this an outer shell, right? So now when I want to do the last scaling, I need to reconvert this into the last one, which will imply that also these U's and R sub 0 are getting rescaled. Okay? So when I do like this procedure, okay, and then I'm flashing just the results, this kind my new R, right, is the one from before. Okay, sorry. Okay, let me write it like this. Let me just do the last step. This B, just the last step and I explain it. This B, let me parameterize it as something like this. Just to linearize. Like I'll quickly explain. So now I do this R goes to some B to the sigma because I had to rescale the R sub 0. The other things have also some dependence and yada yada. So now when I linearize this, I get a linear equation, which is what I call the flow equations. Okay. It's something of the following. You just linearize again, just keeping the first term. Maybe I will just send the notes. And what I wanted to say is now, what we want to look is how these things have changed, right? So it's kind of, which is the derivative, so which is the change after I do one of these procedures minus what it was before, and you get basically, when you have linearized everything, some set of equations that now I quickly explain how to determine. Okay, these are a set of equations. Just give me 5 minutes. Now, okay, I have two variables, which are these rescale things. Yeah, and the new, I have some derivative. What I want to do is now basically look at which are the fixed points, so which solutions are fixed. They don't change when I scale. Why? My theory, again, was self-invariant. So when I should do this kind of renormalization procedure, I should not change my theory, so I want to look which are like what is called the fixed point of the theory. Now, we also want to check stability of this fixed point. I just say it by words, what is the idea behind this procedure. So now I find the fixed points and I find their stability. The solutions, even though I cannot flash them, one of them is the trivial one, u is equal to 0, r is equal to 0, right? Because they were already there. This is the Gaussian fixed point. And it will only be stable when this Gainsbourg criteria is fulfilled. Another one is a bit more complicated, but assuming, so it's my time, so that this is small, which is an assumption I do because at the end I want to compute corrections close to the mean field when mean field is exact, and linearizing that and get a new solution. This is the stable one. Okay, and an stability condition. Now, linearizing these equations are non-linear. No? I have 1 over r divided by here. You linearize things and look at the eigenvalues. And this will tell you when these are stable or unstable. So when this is bigger than 0, we had the Gaussian fixed point, which I write it like this, it should be empty, is unstable, right? We said it should be unstable. So kind of the thing tends to grow to another behavior. But we see that a new fixed point is appearing here, which is not exactly stable. One of the eigenvalues will be stable and the other it's not stable, which is the Wilson fixed point, which kind of now is this how you compute these corrections. And just to flash out the result, now one of these critical exponents, which then you can compute all of them, is related to which is the largest eigenvalue here, and it basically has changed. Okay, this was. Okay, I'm a bit sorry for this. I'll just then flash with words. When you get this one, you can compute all of these, all of the coefficients. If you want, when you get the scaling that I mentioned with this mapping, you can get all of them. And basically, you can now compute all the coefficients. And you've seen that the new effective dimension basically has changed. And I wanted to flash the formula, but I don't have it here. I see, I don't have it. This one. And we see that everything works perfectly, and our effective dimension, it becomes D2. Then again, when I did this Wilson, if you want, I computed corrections to the Gaussian case. So if you remember my definition of G, that was D to the minus 2 minus some, what I call anomalous dimension. This is the final formula you find, which I'm sorry could not find. Get there. And I'm sorry for this, but is the idea clear at least on why the thing has changed? Maybe just some brief comments. With this procedure, with this perturbative method, you could do more diagrams, no? More corrections at the end and get better results. But see, one important feature is that k to the sigma is a non-analytic function, right? So you're never going to get a correction to k to the sigma. And that's basically why it works very well. Of course, given that you are relatively close to the Gaussian fixed point. at the end we're doing perturbative RG. And I had more prepared just in case, because last lecture I was afraid I would take more time, but I could not even finish this part. Is it more or less clear, the message? In reality, it's similar to the first lecture. A lot of mathematics to say the thing is very simple. You have a k to the sigma, you do a k scaling analysis, you understand why the system is behaving as effective a higher dimension.
Speaker? Hello. Yeah, is there any question for the speaker? Maybe you can take it during the break. So yeah, let's thank Daniel again.